Good morning, everybody. Today we are going to talk about wave interaction. This section is number 4 for chapter 11. In the last sections, we have talked about waves and types of waves. We have said that we have two types of waves, mechanical waves and electromagnetic waves. Mechanical waves are the waves that need medium to transfer, but electromagnetic waves which does not need a medium to transfer. Today we are going to talk about the interference of waves with each other. What types of interference are there? We have two types. We have constructive interference and destructive interference. In a constructive interference, individual displacements on the same side of the equilibrium position are added together to form the resultant wave. As you see here, we have a crest and another crest. These two crests are going to overlap each other and produce another crest which its amplitude is higher than the two crests. Here is the interference between the two crests, and here after passing through each other. So now we will move to destructive interference. In destructive interference, individual displacements on opposite sides of the equilibrium position are added together to form the resultant wave. In destructive interference, we don't have two crests to overlap each other or two troughs to interfere each other. We have a crest and a trough. So destructive interference requires two different types of the wave, crest and a trough. If a crest overlaps a trough, we will have a crest or a trough which its amplitude is lower than the two amplitudes of the first crest and the second trough. Okay, now we are going to watch a video to explain the interference between the two waves.
If two wave pulses are traveling toward each other, there will be a resultant wave where the two waves meet. Displacements in the same direction produce constructive interference. At each point along the rope, the displacements due to the two pulses are added together, and the result is the displacement of the resultant wave. Displacements in opposite directions produce destructive interference. Since the pulses are on opposite sides of the equilibrium position, the displacements have different signs, one positive and one negative. When the positive and negative displacements are added, the resultant wave is the difference between the pulses. This is called destructive interference.
Okay, now I have explained constructive interference and destructive interference. Now we will move to another thing. What happens to the motion of the wave when it reaches a boundary? Okay, that depends on what is the boundary state. If the boundary is free, so the incident pulse will be reflected when it reaches the free boundary, but when the boundary is fixed, the incident pulse will be reflected and inverted. So the difference now between free boundary and fixed boundary is that in a free boundary, reflection happens without being inverted, but in a fixed boundary, reflection happens with the wave being inverted. Okay, now we will move to another type of waves which is called standing waves. Standing waves is a wave pattern that results when two waves of the same frequency, wavelength, and amplitude travel in opposite direction and interfere. So, what are standing waves consists of? A standing wave consists of two things, a node and antinode. So, a node is a point in a standing wave that maintains zero displacement, and antinode is a point in a standing wave halfway between two nodes at which the largest displacement occurs. Okay, to be always clear now, this is a shape of standing waves. This point here and this point here is called a node, and this point here is called antinode. In this plane, this is called equilibrium position. Any point at the equilibrium position has no displacement. Node is a point in an equilibrium position surface, so node does not have a displacement, so the displacement is zero at the node, and antinode is the highest displacement, so the largest displacement is at antinode. Okay, our last slide is this photograph that shows four possible standing waves that can exist on a given string. The diagram shows the progression of the second standing wave for one half of a cycle. Here is the beginning of the standing wave after shaking or vibrating the string, and here and here and here is the completing of the standing wave formation. Now we are going to watch a video.
A standing wave is a wave pattern that appears to be stationary. The pattern is caused by two wave phenomena, reflection and interference. Wave reflection is caused by a wave encountering a barrier it cannot pass through. When the wave strikes the barrier, it is reflected back and is turned upside down, that is, it is inverted. Wave interference is caused by two or more waves acting on the same particles. Because each wave acts on the particles independently, their effects add together. In a standing wave, the wavelength and the distance over which the wave travels to a reflected barrier are related. For example, a standing wave is formed in this rope when the rope is vibrated with a frequency that produces a wavelength that is 2/3 the length of the rope.
Okay, that was our content for today, and thank you.